Now it's time to add a new function to your toolbox of pre-calculus functions that you're learning through this course. We've talked about linear functions in pretty good detail. We've talked about quadratic functions and even combinations of those, like piecewise functions and transformations that you can do on function graphs. And then we recently talked about polynomial functions in good detail. Well, the next group are the rational functions. And one of their main graph attributes are called asymptotes. We'll discuss that in great length as we go through this material. First off, a rational function is a fractional function. Anything in mathematics referred to as rational means that it's expressed as a ratio. So a rational function takes the form as a quotient of two polynomials. So this is kind of the generic form of a rational function. And here are three specific examples. Just a polynomial in the numerator, a polynomial in the denominator, and that's exactly what a rational function consists of. Now, this is the first function that we've studied in good detail that has an inherent domain restriction with it. Because these functions are built as fractions, and fractions indicate division, then that means you have the potential for dividing by 0 since you have variables in your denominators. So, the inherent domain restriction, or the implied domain restriction on a rational function, is you must exclude any values of x which cause your denominator to go to 0, because a denominator of 0 means you're trying to divide by 0, and that causes weird things to happen mathematically. So first thing I want to do is to state the domain of the rational functions listed above, f of x, g of x, and h of x. The domain of f, since the main place you want to look for your domain exclusion is going to be right there in the denominator. So the value of x that I want to exclude right here is just x can't equal 4. So since the domain needs to detail every value of x that you can plug into a function, then simply stating this, your domain is the set of all x such that x is not equal to 4 is a sufficient domain statement, because that's going to guarantee that you're excluding the one value of x that's going to cause you to divide by 0. Now there's something special that happens on this graph at x equals 4 that we'll discuss a little bit later. So that's why you need to make sure you can extract the domain of the function first, since that does have a big influence on what the graph looks like. Now for the function g of x. G of x has a quadratic polynomial in the denominator. And since we're looking to exclude the values that make it 0, go ahead and factor it, assuming it can be factored. Let's see, x squared plus 3x minus 10 can be factored as x plus 5 times x minus 2. So there are two values of x that I need to exclude from this function's domain. X cannot equal negative 5 and x cannot equal positive 2. So the domain of this function would be the set of all x values such that those two values are excluded. Just say x cannot equal negative 5, comma, x cannot equal positive 2. And that is the domain statement. You're just telling me what values of x you can't plug in, and that inherently does tell me the domain of x that you can plug in, everything except negative 5 and positive 2. So you're basically taking your denominators and setting them not equal to 0, and then treating that like a little equation to solve. You know, you add 4 to both sides, and you get x can equal negative 4. Same thing here. When you set this quadratic not equal to 0, then you have to set every factor not equal to 0, and that gives me these two exclusions. X can equal negative 5 and x can equal positive 2, because that will guarantee each of those denominators go to, or each of those factors go to 0, making your whole denominator wipe out. The function h of x is the 12x over x squared plus 6. So if I need to exclude values that make this denominator 0, you're going to notice something funny. If you set this not equal to 0 and try to solve it using square roots, you're getting the statement x squared can't equal negative 6. And then if you try to take the square root, you're going to be taking the square root of a negative number. And that means you're excluding complex numbers from the domain. When we're dealing with graphs and we're dealing with, the actual plotting of a graph on graph paper, you're only using real values for your domain and real values for your range. We're not going to use complex numbers as a domain exclusion. So what this means is, if you're only considering real numbers, look at the actual calculation in this denominator. If I take any real number and square it, that's going to give me something positive. Well, so let's just cover up the plus 6. If I take any real number and square it, that'll give me positive the output, or it could give me 0. If I plug in 0, that'll give me 0. But notice what you do after you square the number. You're adding 6 to it. So this denominator never has the chance to be negative and never has the chance to be 0 because of this x squared plus 6. So in the case that you get complex values that need to be excluded, that means all the real numbers are included in this domain. There's nothing of the real numbers that you have to kick out. So the domain of the function h of x is all real numbers. So you can use minus infinity to infinity, or you can use that r with the double thick leg. That's the symbol that means all real numbers. So you're not always guaranteed to have domain exclusions. It all depends on your denominator, and if it has any potential of going to 0, then you're going to have exclusions. But this denominator will never equal 0 because of the squaring and then adding 6. So anything in the form of x squared plus something is always going to be guaranteed to give you an all real number domain without any exclusions. Okay. Now, I mentioned a little while ago that for those functions here that actually do have exclusions like this, something funny happens to their graphs. So let me show you what I mean. I want to type in this function, f of x equals 2x plus 5 over x minus 4, to see what kind of things happen at this x equals 4 location. Okay. Now, a note about syntax: if you're typing in a rational function into your y equals screen, you've got to make sure that you do this syntax. You need a pair of parentheses around the numerator, then you'll use the division bar to represent the fraction symbol, and then you need another pair of parentheses around your denominator. So it should look like this when you enter it. Parentheses 2x plus 5, close your numerator, and then divided by parentheses x minus 4. So that's what your syntax has to look like every time you're using a rational function, because without these parentheses, you're going to do incorrect division. You're not going to be actually dividing the values that are intended to be divided in this function. So if I look at this graph, let's look at zoom 6 for zoom standard. And remember, x equals 4 is an excluded value from the domain. And that's right about here. So something happens to the graph where it comes in here with this continuous curved shape and then goes steeply down, and then somehow it kind of wraps around and comes from above and continues a graph like this. Well, let's zoom out to see if you know what else needs to be considered here. On your zoom menu, select number 3 for zoom out, and then it puts a cursor on the screen as to where you're going to zoom out from. So it defaults to zooming out from the origin. So if you just hit enter, it'll zoom out once. And so you can see the graphs there, and then it makes that jump again. It comes in from the left, relatively flat, and then it curves in here and goes really steep down, and then it comes up here and comes really steep downward again. It continues to kind of level out as it goes further to the right. So what happens when you encounter these domain exclusions on the graph? They produce these graph attributes known as vertical asymptotes. For each x value that's excluded from the domain of a function, you're going to have one of two things happening. You'll have either a vertical asymptote, which is this. A vertical asymptote is a vertical line where the graph jumps to either positive or negative infinity in the y direction. And this is exactly what happens here for this function f of x at the value x equals 4. When you come into x equals 4 from the left, the graph appears to go to minus infinity. And so there's this invisible line, this invisible vertical line there that influences the way the graph looks. And that line occurs at x equals 4. So to the left-hand side of that vertical asymptote, it goes to minus infinity. And then on the right-hand side of that vertical line, so at values like 4.01, 4.1, 4.2, it's coming down from positive infinity and then continues to graph further to the right. So it's almost as though this would be a flat line graph, except for that vertical asymptote that causes it to skew to the infinities on either side of it. Okay, so that's what happens when you have those exclusions. Just to show you, here's another rational function that has two domain exclusions as well. If I graph this one on my calculator, clear out the old one. So parentheses around x squared minus 9, close the numerator, divided by parentheses around the x squared plus 3x minus 10. Close my denominator. Okay? So I should expect vertical asymptotes to occur here at x equals -5 and x equals 2. So let's look at the graph. Zoom 6. Zoom standard. X equals -5 is right about here, and x equals +2 right there. And yeah, check out the graph. The graph's continuous and connected everywhere except for these two vertical lines. At x equals -5, there's that vertical asymptote behavior where the graph goes to positive infinity on one side and then comes from negative infinity in the y direction on the other. And then you have the same behavior over here at x equals 2. The graph goes very steeply to positive infinity, and then it comes from minus infinity and continues the connected continuous graph after you pass that vertical asymptote. Okay. Well, in case you're curious, this one has no domain exclusions, so it should be a connected continuous graph everywhere that you see it. If I graph this one, 12x divided by x squared plus 6, Zoom standard, we have no exclusions, so there should be no vertical asymptote behavior. So this one almost looks sort of like a polynomials graph, but it sort of tapers off on the left and the right, and it's a smooth, connected, continuous curve without those vertical asymptote breaks that take you to the infinities. So that's what can happen. Wherever you have a domain exclusion, you're going to have a vertical line where the graph just jumps to either positive or negative infinity in the y direction. Just as a heads up for calculus, I mentioned here that either this or something else will happen. We're not going to encounter that too much with this class, but just to let you know, you could have a vertical asymptote, which is what we're going to deal with here in pre-calculus, or the vertical asymptotes. But you could have what's also known as a hole singularity, where there is a literal hole in the graph that doesn't produce this infinity behavior like a vertical asymptote does. So an example is this function I've named k of x. So let me cover up my page here for a second and type in the equation for this function called k of x. So open up parentheses for x squared minus 1, close my numerator, and then divided by parentheses around x minus 1. Okay, and now before we look at the graph, what it says, an example of this whole singularity can be seen by graphing this function using Zoom decimal. When you graph it, you actually should see a tiny hole in the graph at the value x equals 1, as opposed to one of these vertical asymptote jumps that go to infinity. So it suggests to use Zoom decimal, which is Zoom number 4, Zoom 4. So if you look at the graph as it plots, yeah, it looks like a straight line. It looks linear. It doesn't have the tapering properties that some of these other rational functions seem to have. But notice right there at its excluded value, which is x equals 1, at x equals 1 on the graph, if you go up to the graph, there's actually a voided pixel right there. Okay, so I mean, the reason I use Zoom decimal is it's a square fit window that actually does allow you to see the hole. If you try Zoom standard, you won't actually see the hole. It'll look like a connected graph. But you know, if you trace it, if you try to trace it to x equals 1, hit x equals 1 and hit enter, notice it gives you a voided y value. But if you trace it anywhere just to the left or just to the right, like if I trace it a little bit left to x equals 0.999, for example, and then hit enter, I actually do get a y value there. It's really, really close to 2. And then if I trace it to a value that's just a little smidge to the right of x equals 1, trace it to like 1.001 or 0001, and then hit enter, yeah, it still gives you a value that's on the graph. But then if you move the cursor left or right, just a little bit, 0.9, I've got a value on the graph. X equals 1, there's no value on the graph. X equals 1.1, there's a point on the graph. So see, that's an example of what's called a hole singularity, where you actually have a hole in the graph as opposed to a vertical asymptote. But again, you're only going to encounter those in calculus. So these occur in calculus, which means here in pre-calculus we're going to be dealing with these vertical asymptotes. So let's continue our discussion on the next page with the next video.